So, hi everyone. It's my pleasure to introduce to you David, who is also the organizer of this podcast. David is a good friend of mine. He's also a staff researcher lead at the Crypto AI lab, where I'm sitting right now. And his research focuses on causality, recommender systems, contextual bandits, and Bayesian inference. He also works on applied stuff, and there his main interest is using deep learning for solving both recommendation and bidding problems. So without further ado, David, I'll let you present a longer version of what you presented last week at RecSys.
Yeah, okay. No, thanks a lot. And if anyone, you can should be able to ask questions in the chat box. And yeah, thanks for your interest. But yeah, so I'm talking today about the why despite all the great machine learning methods we build for recommender systems and bidding and in fact the whole thing, why in fact that we really don't know how these methods are going to work until we try them at A/B test time. And as mentioned, it's there's been I've done a few versions of this talk. I did it at ECML for like 15 minutes, and at RecSys at this fantastic theater, but it was down to 9 minutes. And this is a bit like the director's cut, where it's longer. There should be time to discuss and things. So it's also quite opinionated, deliberately so, because I think it's good to sort of voice what you think and give people all the space they want to push back if they disagree or see something differently. So. And I'll even be a little bit blunt in some places. That doesn't mean, if you shouldn't defer to me, you'd say that seems strange and push right back. So let me move to the first slide. So I just want to give a piece of context before I get started, which I think is interesting, which is in terms of science that we've all been very aware of lately. There's been really two cultures that have been very or two fields that have been very interesting to everybody. Like we're all very aware of large language models, including things like ChatGPT and other generative models, that we seem to be able to train 200 billion parameters without these deep learning architectures, and it seems to work fine. And in fact, better than anyone ever expected, and certainly me. And then we've also been very interested in medicine, and the fundamental tool of medicine is the randomized control trial. And it's probably not obvious what this plot here is, but the idea is it's a graphical representation of lots of confidence intervals, and this black line represents no effect. And so if the confidence interval falls cleanly over either the left-hand side or the right-hand side, it either means that there is a no effect or either there's a negative effect or a positive effect. And when it crosses the line, it means you don't know if the effect is positive or negative. So the point I want to make here is that in the randomized control trial world, we have, let's call it a parameter. It's a treatment effect. There's a difference between two things of one number, and you may not even know the sign of it. And yet in the deep learning world, apparently we can learn 200 billion parameters and estimate all of them. And which one is a recommender system more like? And I would argue that, well, a recommender system fundamentally is tested at A/B test time, and an A/B test is a randomized control trial. So I think it's more like the system on the right, yet we're rolling out deep learning systems as per on the left. So I support this effort. I think deep learning is fantastic, but I think we shouldn't try to win an argument by analogy here. So what is standard recommender systems practice, which I'll argue is more or less a guess and check or shooting in the dark procedure, and it broadly is constructed from these two-stage systems. The first one is using a proxy signal, such as collaborative filtering. So did items, which is a signal that is available before you even had a recommender system. It contains no recommendation. Are items co-viewed in some setting? And more we're using content because of the enormous advances in both images and text. And these can be used then to advance candidates, and then we can advance the candidates, and I'm calling it a contextual bandit. Basically, what you're seeing is are the recommendations clicked on, interacted with in some sense. I'm saying contextual bandit with an attribution heuristic for a specific reason, which is that when you do a A/B test time, you're probably not, and you are doing a proper population split, you're probably not measuring the clicks. You're probably measuring some other value that you are attributing back, but the attribution heuristic is in fact weighting the clicks. And so my kind of opening position is procedure is shooting the dark because you're optimizing something else, and it's all a guess. So this is a clip from an old Pink Panther movie with Peter Sellers. It's a good old but good movie. So my highly opinionated take that you're all welcome to challenge in any play, but it's the shooting in the dark method is in fact best practice. Is not very easy to do better than that. And I think we should be more open about this. I mean, I'm not saying we're not open, but we should be quite open about this. To directly target performance as measured by A/B testing, example with reinforcement learning, is too ambitious, I think. Perhaps we should keep it in mind, but we need to be attempts to say we've solved this and can solve this with RL or other methods can be counterproductive. It's always a bad idea to claim you can solve something that I think is likely unsolvable. Attribution, so that reweighting the value of clicks, I don't think it can be done in a perfectly axiomized way that makes sense, but we probably need to do it anyway. This is actually very related to both points 1 and 2. Part of this talk is actually a defense of click models and an argument that we should take click modeling seriously and do it end to end, and then to point out to some deficiencies that we're doing in click modeling. So I think click modeling is quite possible to do well, but we're not always doing this, and there's clear paths for improvement here. This fifth point is related to all the previous points in the sense that if you note that the learning on the click signal and the reward signal is very difficult, then the collaborative filtering and other methods is actually really useful, even though they're proxies. So these are targeting something else, but it's quite clear we can't do without them. They're very important. But I'm a little skeptical about claims small improvements on say movie lens are real advances. I'm also a skeptic. I'm fairly blunt in the way I'm saying this here, that off-policy estimators based on the Horvitz-Thompson estimator, IPS, which is a very active academic community on. I don't think they work for recommendation where the action space is large, and I don't think they work very well in sequential settings. Part of my reason is I think we'll see that even if you use a method that doesn't waste information, we'll see this method does waste information, you also have a problem. And the final point is actually kind of a more positive one in some senses. We don't actually really need to worry about complex causal theories and confounding, except if you confound yourself, and actually you do need to worry about this. So I'm going to address all of these in sort of different pieces, and I'm actually going to move first to the 7th point, which is somehow the most positive because it's a little bit out to the side, but I think it's useful to address the causal question first. So that's what I'm going to do. So does recommendation need causal inference? Some academic researchers say yes. So here's 2 relatively recent papers. The first is a review paper on causal inference techniques and saying it's essential to incorporate them. The other is from Wang et al. 2020, so it's a few years back, and I actually know the authors of that. They're excellent researchers, and they sort of saying, well, we can never know if you're accounted for all confounders, and this is in fact uncheckable. I don't think this is the case actually in recommender systems, but I'll explain why. And also at the consequences workshop at RecSys, which Flavian was one of the organizers, we had Kieran Gilligan Lee from Spotify. This is a picture from a YouTube talk. It's not the same. It's not exactly the same talk, but it's a very similar talk organized by Olivia Union. You should be able to find it on YouTube if you want to see it. It's interesting. And I wanted to see if I disagreed with anything he said, and actually not really, because he raises a bunch of examples that are not from RecSys and where unobserved confounding problems can actually occur. So the point I kind of want to make, I think is a fairly simple one, is if you're in a recommended system, you're not going to see unobserved confounding. Why is that? Because you're in this very nice causal graph where you have a context X, an action A, and a reward or response R. And the graph looks like this. You're personalizing, so the personalizing means the context drives the action, and then the reward is driven by, is the action kind of in concordance with the context? If it is, you might get higher reward. But everything is fully observed, and the old actions were delivered by your system that can see the X. So they were all caused only by the X because you had them before. So kind of very elementary argument is you're actually in a totally fine situation. It's the same situation that you're in if you're in a randomized control trial. So it's the one you really like. And it just says you can solve the problem with regression to get an individual treatment effect. You just cross the X and the A and regress, and you regress and average over the X if you want an average treatment effect. The hard graph is this one, which is if you have something unobserved. I mean, it's not the only hard graph, but it's a hard graph that you could imagine seeing. And this type of thing occurs all the time if you're doing natural experiments. So if you're analyzing diet and you're seeing people say have eaten something and they have a particular outcome, either positive or negative, but that there could be an unobserved confounder that both impacts the context and impacts the actions delivered. So it's this type of thing that causes a problem. And so in natural experiments, particularly economics, health, nutrition, it's a problem. So broadly, you shouldn't have a problem in a recommender system. In practice, you actually often will, but it's not a problem that really needs to be addressed with the do calculus and this type of reasoning. I'll give you a quick example. So say that you're wanting to optimize a buy and a click, and you have an action A in a context X. So this is all very straightforward. You just want to maximize the probability of both using this, and it's perfectly clear. And then you can typically do this with just two logistic regressions. They're very easy. You firstly build a click model, then you can build a model of a buy given a click. You don't need to build a buy given a non-click because you don't care about that event. You then do an argmax A over the action space here. It's all fine. There's no problems. So far, so good. But what usually happens is not that, but we have some variant, which is instead of this maximization you're doing here, you build you'll do feature engineering, and then feature engineering a little bit different in the two models. So in the click model, you have X prime, and the buy model you have X prime prime, and then you do this. And what you in fact have is that one of your models can see X double prime and B and C or whatever it is, and one is X prime and A. So one model will be confounded by X prime, and the other will be a model and confounded by X prime prime. The problem is the model can see the action delivered, but it can't see but it can't see all the features that led to that action, and that's the situation that causes a problem. So the solution to this, at least from a very clean perspective, is just have the same features everywhere. So there's a legitimate research question here, which is that's not viable in practice. It's a real nuisance to carry around the same feature everywhere and to force all teams to conform to the same feature set. So I don't know the answer to that, but it's, I think, a different type of problem than everyone needs to learn the do calculus. So, and it's maybe highlights other issues, like if you start adding features or removing features from your model, there will be some confounding. If you add a feature, you will likely confound every other model in the system. And if you remove a feature, you'll have a different type of problem. You'll have to wait until some time for the logs to update, and then you'll be okay. So some problems are simply resolved by waiting. But there's sort of things to know around confounding, but broadly not do calculus. As an aside, I have a kind of relatively controversial position on here, which is that causal inference is inference. I'm not going into this too much here, but I have a couple of short papers, a blog post, a long discussion on Andrew Goldman's blog, and two videos on the CritioEng channel that you can look at. Plus, this is easy to get lost, but there was a workshop we ran in 21 that had several presentations, and it's not on the Critio channel, so you'll have to search for it. But it's called Bayesian Causal Inference in the Real World for Real-World Interactive Systems, and it's got quite a bunch of interesting talks and panels on this, which it's worth having a look at. Okay, so that's if we start to saying the causal part is not really a problem, so let's try to target the A/B test performance. Let's demonstrate by example. That's pretty hard to do. But what would it look like, and why do we care? So, okay, A/B testing is the gold standard. It's something we value very highly for good reasons, I think. What is it? It's a proper population split where you apply two different algorithms. Here we have pi A and here we have pi B, and we apply them to different pockets of users, and we get an aggregate measurement of the utility UA, UB. It's got relatively minimal assumptions, so things like sattva impacting users, treatments applied to A don't impact users B, stationarity, etc. And it's very, very aggregate. And this is where the aggregate is useful because it is a thing that you really want to know is here's an algorithm A, here's an algorithm B, which one performs better. But the observations we observe are very disaggregated, and I'm going to kind of drill into what they look like, which is you usually have a user that will view some items. So for me, this is viewing an item is nothing to do with the recommender system. They're just doing something that helps us learn about what they're interested in. Then the recommender system delivers an action. And then there's a response. The response includes whether this is clicked or not, and then some further observations. And then we deliver another action. And there's a response, and maybe a high value response, something like a sale. That might be the thing we really want to optimize. And so in contrast to the causal stuff, which is these complicated graphs, this is actually the main source of our trouble, where we're seeing we learn something about the user, we do something. We learn something, we do something, and we have a sequence that looks like this. This is the main problem that we have, in my view. We can name all of these things. So I'm going to name them just simply H for history and A for action, I to index the user. And then what causes a break here is when there's a request for an action. And a recommender system kind of makes an asynchronous request for an action. And then everything that occurs after that action and between the next request for an action here goes, say, into H1. So it's including the no click and the items viewed, which could be of any number. Okay, so so this gives us a way to, at least in theory, to move between what the logs look like and allows us to write a likelihood of this, at least if we don't, specifying the support of H is pretty nasty, but we just keep it in this very general form where I'm going to leave that unspecified. So H0 is just what the user looks like when they first arrive. And then H1 is what the user looks like after the first action has been delivered and before the second action has been delivered, and all the information we record there. And in this model, we're just seeing a few fairly elementary assumptions that most of them we've already made by being willing to A/B test. So things like sattva, so actions applied to one user don't impact another, and also that actions are kind of conditionally independent of users. And the other one we're having, the one that's sort of not stated, is that we have an arrow of time. So the actions, actions produced at the end, A3, are not impacting H1. So just a sequential nature. So it's pretty elementary stuff, actually. This is a very general model. I think it should be something studied a bit more, actually. And so we can now do a very standard manipulations. The posterior, we're going to see that the likelihood is not, usually is not going to contain that much information. So that's one of the difficulties, but we can do standard manipulations to create a posterior, and it's likely that we're going to need an informative prior here. And so what we had there is the disaggregate analysis where we're looking at the logs for an individual user. We now just switch to the policy. So we have a policy here that is delivering the actions by a convention. These are written as a distribution, but they're not random in the sense of this is something that's determined by us. It is the recommender system. So it's something we get to optimize and find the best one we like. And so this is a way to compute the outcomes we expect for a given policy. And if we apply a utility function that measures these things, so the utility function may say extract out the sales and just count the sales, for example, or count the value of the sales, and then we can do a search for the policy. All very nice in theory. I'm about to the theory is nice. I'm about to sort of show that even a very simplified example of this doesn't work terribly well. So we have a timeline that looks like this. And we have the likelihood contains these products. The first term's not terribly interesting because it doesn't contain an action. It's just what the user looks like initially. This is the first term, the second item that contains an action. So it's the first interesting term, say. And I'm going to then make this really simple, firstly by saying let's only deliver one action at a time. Let's also make it only a click model, nothing more. We're not going to worry about whether a beer, etc., is viewed following it. So the click only has 2 states, and I'm going to make it pretty small. So let's just say we have 1,000 interests and 10,000 actions. So it's pretty small. Okay, so can we just learn this? And what does the click signal tell in this? So well, I'm going to say we have a huge sample, like 100 times the population of Earth. And I'm going to say that we have, so these are the contexts, the interests down here. I'm only going to show the top 5. And these are the actions across here. I'm only going to show the top 40. And I'm going to say that the best action is always going to be A1, just in this case, and it's 2%. And then all the other actions are 1%. So this is like relatively realistic, but small in terms of both numbers of contexts and numbers of actions. So it's fine. These are estimates that you might make if you had 100 times the population of Earth. Let's start to look at more realistic scenarios where we have far fewer people on the system. So you see that even population of USA or population of a mega city, it's completely out of reach. You have no idea that action 1 is better than the others in this situation. What's causing this? It's really the fact that the number of states, we're doing a full cross between the number of interests and the number of actions, and just counting the number of events that occur here. It's a very simple back of the envelope calculation, and it just says, well, and also that this treatment effect, the difference between the best action and the not good actions is quite small. So as soon as you get these types of scenarios, the likelihood function from this part, which is kind of the simplest part, is not very informative. So what do people actually do in practice? Because they obviously do something that works a bit. Well, they, again, kind of, you've already, by advancing candidates, you are, that you're being willing to forward, you've already got some notions of similarity between the context and the action that is sort of being produced heuristically. And so you can, this is usually just called feature engineering. You just put these similarities into a model, and you can fit maximum likelihood, and it works a bit. But ultimately what you have is a proxy or heuristic doing the candidate selection, a proxy or heuristic that is doing the attribution. So that is assigning the value to the clicks based on the real value you measure at A/B test time. The proxy or heuristic that does the feature engineering and putting in the similarities. And then at A/B test time, you'll measure something thoroughly different to all of these things. So we should deeply admire the people that can make this thing work. And maybe there's nothing even better. Like I'm a little bit open to that, frankly, but it is shooting in the dark at this point. So I want to make a bit of a proposal for ways we can use the deep learning stack to handle this without going deep. And I want to, it's worth highlighting that the most standard way to go deep is to put some really complicated model like a transformer or an RNN into the history that will make the context even bigger. That will mean you can personalize. If we're going back here, we can see we have 2 items. You can put some sort of sequential model into here to make that even more complicated and really make the context space even bigger. Well, this would, in fact, would make the problem even worse. So, but I do think deep learning offers some interesting possibilities that we should exploit. So the first one that I want to highlight is that deep learning allows us to build bespoke models. And most problems in recommender systems are actually not just click models that are binary classifiers. And so this is a model we built at Criteo. It's very simple. It's not been published because everyone thinks it's too simple, but it's a very simple way to model recommendations in the real world, which is that we usually deliver more than one at a time. And usually if the banner is clicked on or not, it's usually influenced both by the recommendations and things that are nothing to do with the recommendations. And so the model it encodes some reasonable assumptions. You could question them. That covers the scenario where you show L items And there are L+1 things that can happen. You could get no click, or you could get a click on any of those items. And I would argue that's a pretty common scenario, and it's not covered by any sort of standard model that we use. This is a place where I actually think it's a little bit controversial to insist on having a proper model that turns into a proper likelihood function here. What you often see here is, in fact, a negative sampling method employed. And I think this is a fairly standard shooting in the dark method. And these types of methods, I tend to think they do one of two things. They assume that you're observing a preference, which is like you're saying, okay, item 1 is preferred to item 2. And so models like Bayesian personalized ranking are built on, it's a preference model. But that's actually not what you're not modeling. You're not actually observing a preference. You're observing multiple items that are shown and perhaps an interaction on one and not on the others. So it's not really what you're observing. The other approaches can be to use things that simply don't sum to 1. And why is that a problem? So here fundamentally we have these L+1 things. So we have no click and R1 to RL being a click on any of the items. And importantly, they sum to 1. That's what the normalization here is achieving. And I think this is, to have a pseudo likelihood where the model is not summing to 1 causes a problem, because you can achieve high likelihoods or high pseudo likelihoods not by putting mass on events that happened, but rather by making the model sum to things greater than 1. And that causes a problem. So, and you simply can't do Bayesian inference if you don't have a proper likelihood here. But this is more a critique of what happens in prod, is people putting a proper likelihood here is a bit controversial. So the likelihood-based model is nice, but none of this changes the fact that the click signal that we're seeing is weak. And it's weak because that cross is very, very large. So in my toy example, it was still very, very large. It was 1,000 contexts times 10,000 actions. So the cross size was 10 million. There's no way, even if you're doing random exploration, that you would cover this. And usually you are not doing random exploration. You're doing a certain amount of exploit. And that would also make things harder, or potentially harder, at least harder on the actions that you're not exploiting on. So I said right from the start, and I don't want to sort of contradict myself, the collaborative filtering and other proxy signals are super useful and they do need to be used. And I think the cleanest way to use them is, of course, with a Bayesian approach. This talk can be just viewed as a defensive Bayes, in fact, at least mostly a defensive Bayes. So we can do this using matrix normal priors based on the collaborative filtering. There's very nice work from Ottman Saki from a few years back on how to do this. And the basic idea, this is a plot from Iman Baha, also with my team, who did it. It's very nice, that shows this effect where here we have the independent priors. So the independent prior then is like the original example where we had the full cross and we were not borrowing information between any of the contexts of action. So it's like we had the 10 million entries before. So this independent it's going to be long, say in this case here, so face cream moisture on science. There's no signal on this, so it's long here, it's long here. When it's this length, it means there's been no signal. When it's short, so here in the video game console and on technology and computing, we see it's short. That means that we know this quite well. And in fact, we know it to be good. So we know that's a good recommendation, so that the video game console is a good recommendation on technology and computing. So what the correlated models allow us to do is we can say go to the same action, but on a context that's similar, like science is similar to technology and computing. And we see the models containing correlation, the red and blue lines here, have moved up. And we can even do it to the amazing adventure game. Now, both the action and the context are different. And it's not moved as much away from the prior, but you see both the red and the green lines, which are different priors, have moved away. So that's the basic idea, and it will greatly accelerate learning to do this. So this is sort of my kind of closing argument of why to go deep but not to go deep. I think handling the full likelihood is mostly out of reach. And we should probably like pause on that a little bit because, I think all of us have been very impressed by what LLMs and generative models can achieve. So maybe we should be more ambitious again and say this is feasible, but it's still much more difficult than anything that anybody is attempting right now. But I think we can do much better models with a much better job on click models, blending reward signals and using bespoke models to fit our observation. So we can use deep learning. So something I didn't mention, the deep learning techniques enable both Bayesian inference by Bayesian deep learning, variational inference, and we can build the bespoke click models. Both of them are nice, and it's not standard depth. It's using the technology in a different way. Okay, so I had a bit of a go at the Horvitz-Thompson or IPS Policy Estimator, and I wanted to. This is another break in the talk. I wanted to take a moment to reflect on how I see it and some reflections from a Bayesian point of view on this estimator, and try to be fair, because there's actually a lot of expertise at Criteo on this, and my student and an ex-student is now a researcher at Criteo really pushed the boundaries on this estimator. So, which and have a very nice paper at NeurIPS, and I think they'll present in a session very soon. But my take is much more the Bayesian take here, and I'll just make a few comments on this. So, firstly, like these methods in these IPS policy learning papers, they always make a passing reference to the direct method, which is the method that a Bayesian or likelihood must use, and it's usually just to say it's not good. But there's no choice. And the reason is that the propensity score violates the likelihood principle, and a Bayesian is just not allowed to use it. So what does this mean? Well, the IPS it's the reason is that we've got the what's it called? The propensity score is the probability of an action that the system may have done rather than the action that the system actually did. So the likelihood principle says you should use the action that the system actually did, given you have access to it. And it has some interesting properties. So one of them that I think is worth highlighting is that the IPS estimator estimates that an action that might have been done but wasn't as having a reward of 0. And if you think about this and you say had a logging policy that's epsilon greedy, you'll see that all the time. So you have an enormous number of actions. You have an epsilon, and even if the epsilon is high, of course it can never be higher than 1, and it usually would be much, much lower. Epsilon divided by the number of actions is going to be tiny. And so in most things it's not going to do, but there'll be a tiny probability that it could do them. And the estimator just says, well, that has a reward of 0 because I might have done it. And it doesn't have any regard for the fact that it didn't do it. And so I think that's almost a bit dishonest. And well, yeah, so most actions actually disfavored by the logging policy will actually be in this situation where they likely were not done and will obtain a reward 0. And so 0 is usually a bad reward. You could reparameterize it such that it isn't, and that would have other crazy properties, but usually it's set to being a bad reward. And that just means the IPS estimator really favors policies that cling to the logging policy. Of course, this is the most vanilla estimator, but all the variants tend to cling to the logging policy, or the vast majority. Another point is another way to address the likelihood principle violation, and almost whenever it occurs, is that to note that it uses irrelevant information. So I would say the propensity score is irrelevant. It's the action. It's the probability that you may have done an action when you know the action that was done, and it ignores relevant information like properties, say the embeddings or the properties of both the context and the action. So there are efforts to improve this, but to me, it's efforts to improve something that is really easily done in the Bayesian approach using things like the priors I just described, the blob priors. It's also, I'd like to note the propensity score has actually kind of two quite different uses. Right at the start, I was talking about confounding, and confounding can be, so you can avoid the confounding simply by conditioning on all the covariates or all the context X. But that might be a problem if that's really, really large. And so there's a literature by Rubin on something called a balancing score, but it's just a propensity score. And it's really just using the direct method, but conditioning on the score. And it's a way to handle confounding rather than conditioning on the full X. And there's a different use of it, which is to help in the integration out of the X and to compute an average treatment effect of a personalized policy rather than the individual treatment effect for a particular action on a particular user. And it's actually the second one you need in order to deliver the action, because if you know the consequences of an action on a particular user, you can just find the best one. But this is producing an average. So yeah, neither is actually strictly speaking needed. So sometimes it's said you need to use propensity scores to do causality. It's not true. And indeed, Bayesians should not use it. And I think one reason this comes up is statistical learning theorists don't use priors, and actually instead they put limits on the complexity of the policy. So it's a general thing in statistical learning theory to restrict the space of decision rules, not for a sort of a reason that you can't implement a complex decision rule, but the idea it's more trustworthy if that's restricted. And I think that's a bit dubious. I just want to also mention that there's Fan Li, who did a talk with us, and you can find it on our channel, described a debate between theoretical statistician Larry Wasserman and Nobel Prize winning economist Christopher Sims. Is an epic debate. Is all around this estimator. I sort of I don't understand all aspects of the debate because it gets quite mathematical, and I'm not especially mathematical. But both of them, Christopher Sims is more in the Bayesian camp, and as you see, Larry Wasserman talks about Bayes failing here. I actually kind of agree with Larry Wasserman that these methods that a Bayesian should not use the propensity score, and Christopher Sims proposes methods that he kind of calls likelihood/Bayesian that use the propensity score. I don't agree that you can do that actually, and so I'm in kind of an uncomfortable position of a little bit disagreeing with both on some points, which is I think we should just use Bayes and not use the propensity score. Both of them we have talks on. Of Christopher Sims, there's a talk by Christopher Sims on the Criteo channel, and Larry Wasserman, it's in the Bayesian causal inference for real-world interactive systems channel that I mentioned earlier. And you can find both, and both are super interesting, including also a panel discussion that he's involved in. So I wanted to say something a little bit more gracious about the IPS estimator, which is, I think the worst case for the IPS Horowitz-Thompson estimation is actually the contextual band, and I'll try to explain what I mean. I've kind of conceded that a full-throated Bayesian approach is something we can dream about, but something we can't really implement, which is a method that goes from these logs and then can map it to a policy. And I've kind of noted that modeling these parts, even this first one, even in a very simplified situation, is extremely difficult. And actually, you would need point processors to tackle the others. So something that most machine learning people are not very familiar with. So yeah, I'm kind of noting that that's pretty difficult. The IPS Horowitz-Thompson estimate in this sequential situation kind of can jump a little bit to the jugular, and I'm not going to write down the estimator for it because I haven't thought it through exactly how it looks, but you can go straight to an estimator of the expected utility of the estimator without first learning a model and then doing this kind of complex step. So this is really a two-step procedure. You have the posterior computed here and then the predictive. The IPS is somewhat more straightforward. It wastes a lot of information by using the propensity score, but it is somewhat more feasible in some ways. So I've seen this used not for recommendation, but for much simpler actions. It's the variance still kills you in general. Okay, so that's not so bad in terms of timing. So I'm just returning the points of my argument. So I think the first three, maybe the first four, are really sitting on the fact that that sequential property is very difficult, and the fact that we observe something, we do something, we observe something, we do something, and it causes this complex mapping between a policy and the actual actions delivered, and it makes this problem messy. The fifth point, I don't think anyone particularly argues with, which is just that this reward signal or isn't much on its own, isn't worth much on its own. We really need to augment it with prior information. So this creates a problem that I think is well suited to Bayesian methods, even though it always seems to be a hard sell to use them. I've covered some of my reservations about Horvitz-Thompson IPS style estimators and my discussion about causality. So they're sort of somewhat separate points. That's actually bringing to a close. So actually a little bit faster than I thought, which is good. I don't know if there are any questions, or don't know if Flavin, you want to raise any comments. I have one kind of addendum that I'd like to add to the talk as well.
Thanks, David. Well, I found the talk a lot more balanced than the last time I heard it. So I think already it addressed some of the nuances that I was referring to, because yeah, it felt at some point in time that you were loving and hating the collaborative filtering signal. But yeah, I think now it's I cannot find anything to really disagree with. Yeah, I guess the question is, if you see a future forward for Bayesian models, given the fact that they're so, for sequential actions and sequential data, that could go in production, or you gave up. I guess point processes, right?
Yeah, I mean, as mentioned, so another good talk. I'm really plugging the Criteo channel today. There's another. It's about 5 years ago. Randall Lewis did a really interesting talk on. He calls it bidding attribution. So it's the idea is that if you. So it's not the full reco story, but I think it can be made into it. But if you deliver a display, then things like a sale, he's mostly interested in a sale may happen quickly after it. And if it doesn't, then maybe the display did nothing at all. So there's a kind of, and maybe an interesting idea, which is, I think the way we do recommended systems is mostly kind of epidemiological in that we look at some users, we try something on them, and if it works, we then think that we can try the same algorithm on more users. What I think of as the usual approach to RL is, and even indeed how we live our lives is, do you do level one might teach you how to do level two, right? And this allows you a little bit to be in the between the two, because it might be the same if you wait enough time within a single user timeline, can you learn parameters again of the response to an action if that delay is if the delay is long enough. So the point process kind of gives you ways to do things like this. And I think the temporal information can both be quite important and quite distracting. It's a bit hard to control.
Right. And I guess you want to recruit an intern on this, maybe?
I'm thinking I'm writing a proposal. Yeah, it's a very good point. If anyone wants to work with me on this, yeah, I'll be looking for someone very soon.
I have anything else, and I don't see any other questions.
Yeah, there was just I think it was just a note to say thanks. Okay.
Right.
There's something I'd like to sort of add as an addendum then, which is just a kind of brief comment on the likelihood principle, because I think many people still don't know what it is. And this is kind of a classic example. You'll see it in many books. I don't know exactly who invented it, but the person I know that talked about it is Dennis Lindley, who's a famous Bayesian statistician who died a few years ago. And the idea is, if you say you flip a coin 12 times and you get 3 heads and 9 tails, the likelihood function is so theta being the probability of the coin, or in the example, I think it's a pin because maybe it's not. Maybe we think coins are going to be half, so it's something that could not be a half. So then it's theta cubed times 1 take theta to the 9, and that's all the information in the sample according to the likelihood principle. But there are two ways you could consider computing a p-value on this, which is a frequentist method. One is to say, well, if we do 12 flips, the probability of getting 3 heads or less is 0.073, and if we flip until we get 3 heads, the probability is 0.006, and that actually becomes significant in a kind of standard frequentist way, or by kind of conventions. And so you can compute that with a negative binomial draw if you want to check my calculations. So in the kind of famous paper, Dennis Lindley sort of joked he wasn't using either of those stopping criteria. He was saying I'm sampling until the coffee's ready. So why am I talking about this? Well, I want to jump to a machine learning example and to talk about statistical learning theory. And so here we have like a decision boundary and 2 classes, the blue circles and the yellow triangles. And according to a statistical learning theorist, using logic very similar to the p-value, the statistical learning theorist wants to know how the boundary was created and what boundaries will be created on other data sets. And that's the kind of I think once you look at it like that, it doesn't make much sense. I think it's a kind of crazy hypothesis that the size of the decision space that you drew from impacts the performance, but that's fundamental to statistical learning theory. And this is just a standard Bayesian frequentist argument. So there's a famous paper by Edwin James, Confidence Intervals versus Bayesian Intervals. It's very combative and shows how stupid frequentist results can be when you're not based on sufficient statistics. So I think that's an interesting way to look at statistical learning theory. Okay, any further comments or questions? Otherwise, we can wrap up.
Not on my side.